great pleasure to be in this community that I feel at home at, and to hopefully have you learn something today. So what is a continuous variable or bosonic quantum system? It is characterized by continuous degrees of freedom, such as the position and momentum of an oscillator, or the mechanic or the quadrature components of an electromagnetic field mode. They're often called I or Q. There's kind of 4 or 5 or 6, depending on how you count, different experimental paradigms and quantum platforms that utilize, that are modeled by such systems. And including optical fiber free space communication, as well as microwave instead of optical cavities, but in addition to optical cavities, microwave cavities. And more recently, there's these kind of technologies have arisen, and you'll be surprised what people can do with them. So basically what I'm saying is that why should you care about CV systems is because, well, they're already here. We already use them, especially the fibers. Okay. And right, and any system or many systems that you consider as 2-level systems do have higher excited states that in principle can be used and can come from a continuous variable system. So there is more space to use there. And you all know space leads to more potential for redundancy. So it might be useful to use higher lying excitations of current systems that people already have in the lab. Of course, and why should we, besides the fact that they're already here, there's also other fun things about them. So there's a practical thing about this lifetime. Some of these cavities have very long lifetimes, have been designed with lifetimes in mind. Similar to this point, there's atomic systems and some molecular systems have these degrees of freedom naturally there. Instead of being higher lying, they're now just encoded in the vibrations. And the vibrations can potentially be used for something because there's a Hilbert space there. And it's also just kind of fun. You know, there's continuous stuff. If you get bored of bits and discrete things, this is the way to go. There's kind of a handful of interesting things mathematically or operationally that I've collected. I don't want to go through all of them, but just for the YouTube, mention them. So you will see some of these throughout the talk. So for example, there will be certain states that can be used as resources that are kind of like above the easy set of states called Gaussian states. Things you can do in formally infinite dimensions, they can circumvent things that have been proven only for finite dimensions. In particular, there's a C0 gate that cannot be connected to identity in 4 dimensions and finite dimensions, but in infinite dimensions that's possible. Transversal gates, East and nil doesn't work in infinite dimensions. Depending on how you measure, certain continuous variable codes sort of utilize fewer resources than discrete variable codes. You'll see that a little bit too. Okay, so what is, so a little bit of some physics hand waving to get you a flavor of what is a mode. The word mode is highly overused, so it's important to kind of define it. So we go back to classical physics. We have a box, you know, we solve Laplace's equation in the box, and we have these things called normal modes, right? Everybody likes those, right? Even the computer scientists, right? Good. Okay, so we have these normal modes. Okay, are these our modes? Well, sort of. Let's sort of back up and write what you would think would be a classical signal in terms of this basis of modes, basis of normal modes. It's a linear combination. There's nothing quantum here. Okay, linear combination, not as quantum superposition, and the coefficients here, in more generally, can be complex because electromagnetic fields kind of have 2 quadratures. So I'm just going to sneak that in. You can think of it as R2. You can make it real if you're more comfortable with that. So this is basically what a signal looks like. It can be sort of it can be as a function of time, or it can be as a function of space in a box, or as a function of time going through some fiber. Doesn't really matter. And let's see what it would look like in the quantum state space. So so these types of signals in quantum state space are represented by a very, very important, very specific kind of state called a coherent state. And if you were to write this signal in quantum state space, it would be sort of related to, or kind of equivalently expressible as this tensor product of coherent states. And if I were to draw the coherent state as a function of the two continuous variable degrees of freedom of this system, the position, the momentum or the position, the coherent state is nothing but a Gaussian centered at the point alpha in this position momentum space. It's a Gaussian because of Heisenberg uncertainty. You can't measure position momentum to the same precision, and so you wind up having this kind of blob. Okay, the coherent states are what I want you to think of as sort of the analog of a classical signal written in the quantum description. Okay, and if there's any questions or nods, that'd be great. Yeah.
So, how many particles are there in this last thing? There's this thing you wrote about for one particle, right?
So there's n modes here, and each mode has certain. We haven't gotten to particles yet. Each mode has a certain energy. The energy is roughly alpha squared. Okay, we'll get to particles when we quantize, but this is classical.
Okay, so you're just using this tensor notation to describe something classical.
Yes, exactly. Exactly. To kind of link back to old school. Yeah.
What's the number of the FIs in the FJs in the second like in the quantum?
So they define.
Okay, in the classical one I see, but the quantum one, what's that?
Yeah. They define the actual Hilbert space via quantization, which I swept under the rug for this slide, but we'll get to later. They effectively define what your mode is. Okay. There'll be another slide, and ask again. There's the other slide. Now we're going to quantize. So a quantum mode arises from quantizing the amplitude of each classical normal mode. So you take every one of these, and you now can quantize and make discrete yet another thing. So there's two discretizations. First is you solve Laplace's equation to get the modes. Each mode then gives you an L2 of R Hilbert space, which you can define in many, many different ways. But in this case, like, you can kind of heuristically think of the amplitude of the mode being quantized. So this gives you a copy of L2 of R inside each of these. Okay, and that was the tensor products that I've defined implicitly in the previous slide. So this allows us to consider more general states, because now we're not just thinking about coherent states. That's not the only thing we can send. We can now consider many, many, many different things, including, for example, the simplest sort of extension, superpositions of coherent states.
So it's like quantized L2 of R, not L2 of R, right? L2 of, I mean,
well, so it's kind of like going, the alphabet was R, the coherent states are kind of R, and quantum states are functions over the alphabet, so L2 of R. Okay, so let's consider superpositions of coherent states. But in what way are we going to consider them for error correction? Well, let's first go back and look at how we did this, how we can do this for binary case. Classical code words, to me, so there's a canonical way to upgrade classical to quantum. And you can do this as follows. First, you remember that classical code words are kind of just a packing problem. You space them around in a sparse enough way so that whatever errors move them around won't move them too close to each other. So there's here's some couple of classical codes where you can still have a nice geometrical picture, more or less. And you see these things are spaced apart, and so the distance is like half of the spacing. Yeah, preaching to the choir. What do you do to upgrade it to quantum? Well, and we're going to be using some continuous things, so we can similarly do this on a lattice, and we can do this on a sphere. Okay. So to upgrade to quantum, we have to superpose these classical code words because we have two sources of noise. We not only have bit flip noise, we also have noise that induces relative phases, because in quantum, we're storing quantum information, and we have to worry about phase flip noise. And the way to protect against phase flip noise is to superpose. You'll notice any quantum code, the code words are going to be superpositions of some basis state. There's no way around it. So you basically, okay, for the repetition code, there's nothing to superpose if you want to store a qubit. But for single parity check, you have to have basically a clever way of dividing this big set into little sets and superposing elements of the little set. This is called the CSS construction, basically. And so you can block them by color here, and you see that this is a way to get the 422 code. And similarly, the same type of idea can hold for the continuous variable case, now using coherent states as the element that you're superposing, as the basis. Okay, here we use bit strings, and here we'll use coherent states. And it works. If you take the lattice and you split it in a checkerboard type configuration, superpose all black, superpose all white, you get a quantum lattice state or what is known as a GKP state. If you do this on a sphere, you take your favorite spherical code, find a way to partition it into, say, 2 or something, many copies, superpose, you get something that can be defined as a quantum code with bit and phase flip protection. We call it quantum spherical code. And coherent states are sort of one ingredient that you can use, one type of basis that you can superpose, and in this way construct quantum codes from classical codes. But we're not done. My talk would be done now if the coherent states was the only basis, but there's many, many more. Yes?
So just make sure I'm understanding these images properly. So basically, I view every color as corresponding to one code word, and like the superposition over those colors is the encoding of.
Yeah, that's right.
Yeah.
That's right.
Cool.
So this one was the only one that didn't have a logical qubit.
Each ball is a coherent state. It's a Gaussian.
Each ball here is a coherent state, yeah. Right, and the formula is up here.
Is it a problem with orthogonality?
It's Gaussians. Don't worry about it.
Well, I guess the point is approximate orthogonality is good enough.
Yeah, the overlap between two coherent states is exponential in the Euclidean distance between them, between the points labeling the coherent states. And yes, you have to deal with it, but for coding theory perspectives, it's okay. Yeah, ideal codes are fine. Okay, but we're not done. Okay, so coherent states are these points, and we can use them. We can naturally plug in our classical codes via CSS type construction, but we're not done because there's many, many different things we can do now. So remember, we've quantized our modes. Let's fix. Yeah. So more generally, what can we do? Well, more generally, a single quantum state is a function in L2 of R, so it's normalizable. But it's not only just normalizable. I claim it also needs to have finite energy. So and energy variance and whatever other moments it has. All of these things should be finite. So there's this sort of distinguished operator called the number operator or the occupation number or the energy operator. Just think of it as energy. And you just want all your energy moments to be finite. And this actually defines the state space to be Schwartz space. And I think experimentally and theoretically, we all are working in this Schwartz space, whether we like it or not. We often don't say we are, but I have yet to find a counterexample. So the real state space shouldn't be L2 of R, it should be S of R. And for the codes that I'm going to consider for the rest of this talk, often happens to be the case that I'm actually going to be using things that are not even in L2 of R. I'm defining codes in terms of basis elements that are not normalized, not normalizable even. Don't be scared. It's okay. Because as I said before with the coherent state picture, there's very controlled ways to regularize these things, and everything works out in the end. This is something is necessary to do if you're actually going to build these things in the lab. But from the coding theory perspective, the properties that I'll describe with the idealized versions carry over naturally. Yes?
Storing to truncate. I mean, this truncate to make them non-finite.
They become approximate, right? Like transversal gates, the continuous families of transversal gates exist for codes whose code words are not normalizable, as those are the only examples I'm aware of. And then if you just kind of regularize them in a nice smooth way, the error correction becomes approximate. We have a paper about that. Okay, so there's many, many things we can do. We already covered a little bit our coherent states, so we're kind of already good. We can make some quantum codes, but what else can we do? Well, we can construct other bases. And how do you partition a plane? Well, you can think about it in terms of lines. Okay, so Cartesian, think Cartesian, right? X and Y. And so what is this? Well, these states, X and P, are states of fixed position and states of fixed momentum. And if you draw them, loosely speaking, in this sort of phase space of this system, these are just lines, horizontal and vertical lines. Each of these forms a basis, and they're conjugate to each other via the Fourier transform. Likewise, you can do a polar decomposition. I'm not going to use the word polar because polar codes, not to confuse people. If I call it angular, you can think of circles and rays. Okay, you can think of angles and radii. So the circles are Fock states. Okay, those are called Fock states now. You know this now. This n, I think, is roughly the radius. I don't remember if it's square root of n or n. Doesn't really matter. You're going to tile with these circles. This forms a basis. Alternatively, there's a conjugate basis to that, which are called phase states, which are rays. And they're rays at each angle. And so they're parameterized by an angle. So this is a kind of an angular decomposition of the oscillator. And the important thing is this playground is very fertile. Each basis can be used to define codes in some way, in some spaced apart way with proper superposition so that you have phase error protection. Right. It also offers a way to connect to other codes, as I said before, with the coherent states. And each basis offers a way to understand how errors occur. So there'll be physical. So in bosonic coding, what often happens is that there's actual physical noise, and then there's these idealized operators associated with each of these two pairs of bases, called an error basis, that you can expand noise in terms of. In qubits, this happens with Pauli's. You can expand any noise operator acting on qubits in terms of Pauli strings. A similar thing happens here, and now there's two ways to do it. So let's cover the Cartesian first. So there, the basis is, a nice error basis consists of displacement operators or shift operators. They move the position or the momentum of your oscillator around. And they're exponentials in the position or the momentum, or if you like to write the position plus or minus I times the momentum, the lowering or the raising operators of your harmonic oscillator. So think of these as the simplest possible operators you can have. They are basically the closest analog of Pauli strings that you can find inside the oscillator. And they are orthonormal in the Dirac sense. Again, don't worry about it. It's fine. Just think of this as the usual Kronecker sense. And any bounded operator can be expanded. Say U can be expanded in terms of these displacements with some coefficients. The coefficients will be finite if the operator is trace class. And now, so these Ds, they're kind of like Pauli's. What distance do we use for Pauli's? The weight. Right, so you have some displacement in some end mode space in the positions and the momenta. How many modes is this thing acting on? Okay, and this distant natural notion of distance also can carry through, and you can develop codes against this distance. And these are called analog stabilizer codes or Gaussian stabilizer codes. And these are the closest analogs of your NKD qubit codes. So let's kind of sketch one out here on this side. But first, we're based on the 4-qubit code, the 412 qubit code. It encodes one physical qubit and one logical qubit into 4 physical qubits, distance 2. The code words here you can write in this way. So these are just, the thing inside here is a Bell state, 0, 0, plus or minus 1, 1, and you just copy it over twice. And these are the code words of this code. So what do you do in the continuous case? Well, everything just goes to reals. Okay. This is you copy y twice. You do the Fourier transform with x. You're integrating here over the reals instead of summing, and you do that 2 times. And this gets you a 412R code. It encodes one logical mode into 4 physical modes, and it protects against displacements acting on at most one mode. This is a mode, meaning it's an infinite dimensional Hilbert space. Okay. These codes have infinite dimensional Hilbert spaces, logical Hilbert spaces. The stabilizer generators naturally also carry over. These are your favorite 412 stabilizer generators. And now if you kind of think about Z as the position and X as the momentum, then you get the same kind of structure here up to some signs, which you already start to see if you were to write this down for qubits anyway. Now, these codes have infinite dimensional logical Hilbert spaces. Their stabilizer group is continuous, so any power of this is in the stabilizer group, as opposed to just Z2 powers of these. So, because we're continuous, we can actually drop down and look at the Lie algebra. We don't have to look at the full group here. And this is what often people like to do. And so you can see, you can just peel off the generators off the top here and write them in this way, and study this code in terms of these, what are often called nullifiers. And the stabilizers stabilizing the code is equivalent to the nullifiers annihilating the code. because they were in the Lie algebra. E to the I0 is 1. And here's an equation kind of showing how one of these nullifiers will annihilate the code. Because both of these have y, so you get y minus y because x1 acts on the first mode, x2 acts on the second mode. These codes are not very useful. I'll explain why in a bit, but there is a niche for them because they're very connected to measurement-based, continuous variable measurement-based quantum computation. The techniques and tools used to study these codes are very useful in that domain, and that's still something that's actively explored. So why are they not very useful? Well, because this notion of distance is not very good applicable to bosonic systems. Because in reality, every mode gets some displacement. Maybe it's small, but basically noise operators generically will act on every mode. And so there's another metric that's a little bit more physical that basically is the total length of the displacement. It doesn't preclude the displacement from acting on any mode, but it forces it to, like, the displacements that you can try to correct have to be sufficiently small. Okay. And this now is relevant to this other class of lattice codes or GKP codes. So I had mentioned already GKP codes when I placed them on in terms of coherent states. There's an alternative formulation in terms of position states, which are these lines in the phase space as opposed to blobs. And in contrast to analog stabilizer codes, whose stabilizer group was infinite and continuous, the stabilizer group here is infinite and discrete. Yes?
So can you go back for a sec? In the discrete case, it's true that correctable errors form a vector space, right? Like if I can correct E1 and I can correct E2, I can correct alpha E1 plus beta E2. Is that not true in the CE case?
For this?
Well, I mean, you're saying that Hamming weight isn't the right, well.
Physically, I'm saying the Hamming weight is...
Yeah, no, I can see why, but I'm just wondering if that statement breaks down in infinite dimensions.
the vector space.
Yeah.
For this one, I doubt it, but you know, I don't know. I can't answer live during the talk, but I bet you it works here. I'm not so sure it works here. Yeah, that would be my... Thanks. So the stabilizer group is infinite now also, but it's discrete as opposed to continuous. And as a result of it being discrete, or in correlation with it being discrete, the actual logical dimension is now finite dimensional. So this is now a way to encode qubits. And these codes are compatible with the second metric in the previous slide, namely the one that protects against sufficiently small position momentum displacements. So how can you get an infinite but discrete stabilizer group? Because position momentum don't commute, we have to make sure that all the stabilizers commute. Well, how do you do it? Well, you can even do it for a single mode. All you do is just shift in position, or sorry, shift in momentum and shift in position by specific values that are like basically, you know, square roots of 2 pi. Because the commutator between them will multiply these two values. So if you go around in a loop, you get a phase that's e to the I times these two coefficients. And if these two coefficients are multiplied to a multiple of 2 pi, the phase is 1, and you have commutation. So these are commuting operators, which you can verify. And these generate the translation, or the group of symmetries of a square lattice. And their joint +1 eigenstates can be written in terms of position states as these two kind of position cones. It's very interesting that Professor Calderbank was telling me yesterday these types of cones are very common and potentially be useful in wireless communication when you write them not in position momentum space, but in terms of frequency and time. Those are, again, conjugate variables in the exact same way as position momentum are in the quantum case. So these position state cones offer another way to write your lattice GKP state. And the equivalence between these two is still mind-boggling to me. So if you're confused, I am also confused. But I want you to share my confusion because I want somebody to figure out, you know, why this happens to be the case. But if we go back to the position state formulation, the same type of coding theory thing works here. You wind up having interleaving cones. If you have a position shift, as long as the shift is not too large, it can be detected, and if it's a little bit smaller, it can even be corrected as long as it keeps each comb within its unit cell. And if you can alternatively write these in momentum state space and figure out the same picture in momentum states. Okay, so that's our lattice codes. There's a third class of codes that has to deal with degenerate lattices, or lattices that don't fill up the entire space of your modes. So you can get these by considering a GKP code. It's a full lattice in your N modes and just removing some stabilizers. And this winds up giving you another very interesting class of codes. This actually drops the physical qubit restriction and allows you to protect an infinite amount of logical information in your code now. But it still protects against sufficiently small displacements as the original GKP code did. And these are called GKP stabilizer codes. And it's a very interesting example of something some people hadn't thought was possible, that you could store infinite dimensions worth of information and still protect to some degree against displacements. One way to consider them or to write down or to understand them is to consider their encoding circuit in the context of the previous analog stabilizer encoding circuit, because now both codes map physical modes into logical modes. And both circuits start with some physical K-mode state, initialize in the rest of the modes in some particular state, and then apply a Gaussian or standard kind of unitary, which is your analog of Clifford unitary here. And the main difference is the state used for the ancillas. Here, it's the 0 position state, and here it's the GKP state. So if you use a line, you get analog stabilizer codes. If you use a lattice, you get GKP stabilizer codes. It's this lattice. You can think of it in one of two ways: as a lattice of coherent states, or as a comb of position states.
No, because GKP is also the code, and they're encoding.
Oh, yes. Sorry, I had the clarification. This is how you have you have stabilizer codes and you have stabilizer states.
Okay.
This is the one with the This is a stabilizer state. It's the lattice with square root of 2 pi instead of square root of 2 pi n. Smallest lattice you can get. Yeah. Good. Thanks. Good eye. So those are your Cartesian codes. Let's cover some angular codes. Remember, we had circles and rays, Fock states and phase states. And before I cover the Fock states and phase state codes, I want to remind you that there is an actual bona fide angular system that exists out there that actually Christoph's going to talk about, that is not what I had defined as a continuous variable system, because as opposed to the continuous variable system's position and momentum both being continuous, in this case, this system of a particle in a circle, the position degree of freedom is continuous but compact, and the momentum is infinite but discrete. Okay, so this is another Hilbert space. Call it a planar rotor that has a bona fide angular degree of freedom. And the reason I'm telling you about it is not only because Christoph's going to talk about it, but also because the angular decomposition of the oscillator actually mimics the angular nature of this space up to some degree. And so I want you to know that about this space, so we can kind of take this space and graduate into the oscillator and take some of its intuition with us. By the way, this space also has a Clifford group that we've been furthering a bit in this paper. And there's lots more to do here that's already been done here and here, in case anybody's interested. So there's a bona fide planar rotor that has angular degrees of freedom. And then the oscillator, in this understanding or in this formulation using these two bases, forms kind of a fake number phase, let's call it a number phase rotor, that mimics the properties of the planar rotor. And how does it mimic it? Well, the phase and the Fock states themselves are position and momentum states of a rotor. So you can think of this is labeling angular momentum, and this is labeling angular position. The angular position label is perfectly kosher. They're both angles. The angular momentum label is not. For an actual rotor, you can spin one or the other way, and there's a sign. You can have positive, negative momentum. So the momentum is an integer. For the Fock state, it measures occupation number, so it starts at 0 and goes up. So there's no negative momentum. And that's the key difference that obstructs you from fully embedding a rotor in an oscillator and having those be actually the same space. But a lot of the intuition from the rotor carries through nonetheless. So, for example, if you go up to the operator level, the error basis for this consists of, again, displacements. But now they're displacements in Fock state and displacements in position. Displacements in Fock state are these things that are sometimes called phasers or Susskind Glower phase operators. And they're basically the same thing as raising and lowering operators. They add and subtract photons, but there's no square root. If you don't know what I'm talking about, don't worry about it. For all intents and purposes, these just move you around in momentum. They add or subtract momentum. And then things that move you around in the position are just actual rotations generated by your canonical energy or occupation number Hamiltonian. And the eigenstates of these are the Fock states because they're circles, they're invariant, right? And they just give you some phase. So these are your position and momentum shifts of your fake number phase rotor. It turns out they also form a complete basis. It's not as orthonormal, it's not as nice as the displacement operator basis, that's true, but nevertheless, there's still some intuition there, and you can, in principle, expand any operator in terms of it. So, what can we do in this case? Well, we can play the same game on the circle as we can play on the line. So, I constructed before GKP codes on a line. Now, if I just wrap the line back up, and then I have this pizza, and I can, interleave cones on the pizza, right? Even odd slices. Superpose them again, and get logical states. And these correct against, again, small shifts in both quadratures in position and the momentum, just as before. It doesn't matter if one of them is discrete. The same kind of intuition works here. And those were codes that you can define for a bona fide rotor. And the point here is that they can also be defined for an oscillator. And in this paper here by these three authors, the number phase codes were defined in this way. And so they're kind of a polar analog of GKP codes that you can embed inside the oscillator. They protect against those basis elements that I showed you before. And if you express their logical states in terms of the phase state basis, then they're just, they form two very small Mercedes-Benz-like cones in terms of the phase space that are interleaving. If you, so therefore, they protect against sufficiently small rotations because they're spaced apart. And if you now define an alternative basis that's just superposed versions of these plus minus basis and express that in terms of the Fock basis, you'll see that they form two interleaving cones in the Fock basis. And therefore, sufficiently small momentum kicks are also protected because the cones are spaced apart in the Fock basis. So these are very much, as close as possible of a stabilizer-based analog of a rotational code inside the oscillator. And the noise operators I showed you before, the rotations and the phase operators, position momentum kicks, they can be thought of as more or less some stabilizing type, in a more or less a stabilizer type formalism. However, because of these complications, this negative momentum, they don't form a group. So you can't dagger them and get the same thing because, but there is still some remnants of the stabilizer formalism that could be developed further potentially. Yes?
Does it really matter if you have to stick to a group here in like make it more expressive as a component? Like
I think it's without inverses, so whatever that is, a monoid or semigroup.
Probably a semigroup.
But I think in math, they actually call that a monoid.
well,
Yeah, we've been using it wrong.
yeah.
But anyway, whichever it is,
It has all the properties except the inverse.
Yes.
correct. It has all the properties except the inverse, and it hasn't been studied. This is as far as I know. This is as far as I've taken it. So that's another sort of open thing that, because we love the stabilizer formalism. We want to salvage as much as we can. But. Okay, so we have our rays, in phase space, kind of angular version of GKP codes. They're spaced apart, but they're not normalizable, okay? The rays are not normalizable states. So we have to regularize them in some way, as I mentioned before. And one way to regularize them is actually yields these famous cat codes. If you now take your ray and instead of, this ray is an equal superposition of all the Fock states. If you now dampen it with a Gaussian and add this guy here, you get what's called a coherent state. We're back at our Gaussian blobs here. So you substitute each ray with a blob, you gain an extra parameter that now quantifies the radius of the blob, but you maintain the same level or a similar type of protection, because now instead of rays that are spaced apart, you have blobs that are spaced apart. So there's still some protection here. So these CAD codes also allow you to protect against the same type of position and momentum kicks as the phase state codes. The simplest one is one where you just have alpha and minus alpha for the logical 0, the logical 1. This is called the two-component or two-legged CAD code. And one thing I want to mention with that this comes with not a stabilizer formalism in any near conventional sense. So we're not even a group, not even invertible or diagonalizable even. Okay, but there is something very interesting that comes from a long history in quantum optics, where these two states, this whole space, is actually stabilized by a double well potential in the form of a Lindblad master equation that attracts you to these two states here in a quantum way, meaning that it can sometimes preserve superpositions. And so instead of a stabilizer formalism, you get this kind of dynamical stabilization scheme that actually has been implemented in the lab. So in this case, we are forced to graduate from the stabilizer formalism and deal with lowering operators, which are not nearly as nice as these unitary Paulis that everybody loves. But there is still something here stemming from physics that should be explored from the coding theory perspective. Just some more references on the CAD codes. They have potentially deep connections to the repetition code. So to me, they're kind of analogs of the repetition code in the discrete case. And if you arrange repetition code in a nice 2D lattice, you get classical self-correction because the growth rate of error bubbles will be suppressed. And so similar types of things have been attempted to be explored for the CAD codes, which to me is very interesting. And the CAD codes are the ones that realize a C0 gate that's connected continuously to the identity. These are the two-component CAD codes, the simplest ones, and then the four-component ones now actually have each logical code word as a superposition of two coherent states, alpha minus alpha and I alpha minus I alpha. And now you have protection against momentum kicks, as I mentioned before, with the phase state codes. So the more coherent states you have, the more protection against momentum kicks you have. And the shorter your minimum distance between the two coherent states goes, so the fewer rotations you're able to correct. And this four-component CAD code, the first one that actually corrects against both some bit and some phase, some kicks and some shifts, was actually realized, and this was demonstrated in the first break-even quantum error correction experiment in microwave cavities. So it's probably the farthest code from the stabilizer formalism that you've seen so far. From a theory perspective, it's kind of not very conventional, but from the experimental perspective, it's actually presents very rich and very realizable physics. Okay, there's the third class of codes. We had our lines, we had our circles, and I'm still not done. These are called Fock state codes, these are finitely supported codes that you can embed using the Fock space of the oscillator. So one way to get one of them is to take our favorite, again, 4-qubit code, 412 code. These are its code words. And now we can just kind of naively embed them into the oscillator by just adding up all the bit string elements. Okay, so here you get 0, here you get 4, here you get 2, here you get 2, and you can map that now into Fock states. And when you map that into Fock states, what have you preserved? Well, you preserved the Hamming distance between these states, and so you have preserved the same kind of, you still have some sort of spacing now. Now it's in Fock space, but there's still spacing, so there's still error correcting properties. This code is called the binomial code. And you can think of it as a finite version of the CAT code. So while the CAT code was a regularized version of the phase state code and the number phase code, The binomial code is a rigidly truncated and then regularized version of the number phase code. And as I mentioned, there's still some spacing in Fock states, so you're able to protect against shifts in Fock state number. And more generally, you can develop these types of codes, and you put the coefficients here from the binomial distribution, as you put in here, because you also want to protect against some degree of what stems from the rotation errors, the position state rotations that I mentioned for the phase state codes before. So binomial coefficients allow you to do that. And so you get this kind of extremely discrete family of codes. And you can play these games in higher dimensions as well, or larger number of modes. So that leads you to this large class of Fock state codes. You can kind of imagine that there exist 2, 3, 4, etc. mode analogs of these things. And these codes are specifically designed for a noise model where the most prominent error is a kick down in the photon number, not up, but down. Physically, that represents loss of photons leaking out of your mode or cavity or fiber. And if you look at how those losses act on the modes, you'll see, beautiful patterns that they shift you down depending on which mode lost the photon. And so you can try to play games where you space apart your Fock states in a way that when you lose sufficiently few photons, they're still correctable and detectable. If anybody knows what a Dickey state is, it turns out that the same type of binomial coefficients also allow you to protect against or to develop codes that are now expressible in terms of these Dickey states. These are just states of some this many ones and the rest zeros symmetrized over everything. And there's many other codes. The most canonical one that was probably the first one that was formulated is this error detecting code that detects one loss, right? But doesn't correct it, called the dual rail code. And this is still used in photonics every day as sort of a code that they post-select on. If they see a click, then they know they can't use it because that means the photon was lost and the information was lost. And there's very many interesting exotic codes that people have recently looked up. So people have recently developed that you can look up on the zoo, including things stemming from high energy physics by Brian Swingel's group and some other field theorists developing coherent states in this multimode space, as well as somebody showed that Penrose tilings have the properties that satisfy them from being an error correcting code. Similar, I guess, to, well, I don't know how that works. I don't want to comment. So there's the zoo of codes. Now let's finish a little bit by looking at the syndromes and the noise. What are we supposed to measure? So in stabilizer formalism, we measure stabilizers, right? What are those? They output bits, right? Our bits help us detect which error space we're in and then correct. Here, the syndromes have to be continuous for the continuous codes, and sometimes they can be discrete for these other kind of angular type codes. And what are kind of the syndromes? Well, the key word I want you to take away is the word modular. If you just measure the position, you project onto a line. And if you have a lattice, you want to maintain the logical superpositions of the two lattices. And so projecting onto a line is going to kill everything. So figuring out the position exactly is going to be too much information. What you want to figure out is where the lattices have moved after a shift. And that requires measuring the position modulo the lattice spacing. Okay, so you don't want to know the entire information about the position, you want to know only some part of it. So you measure it modulo something. If you're on a Mercedes-Benz and you're moving like this under noise, you've moved over here. If you measure the precise position on the circle where you're at, you collapse these two superpositions and you're left with only this one. And that kills your logical information. So what do you want to know? You actually want to know the angle modulo the spacing between the code words. So you have to know the modular angle, okay? So, and you can phrase qubit information as well in terms of kind of a modular picture, but the point here is that you see the word modular mentioned in many, many different places. So whatever classical kind of position, momentum, phase, number, quantities that you develop measurements for, you have to measure them modulo something to preserve the code space and detect and correct errors. And what does this mean? Well, even though the information is modular, it's still continuous. Position modular lattice spacing is still a continuous number. So you need an ancilla that can spit out a continuous number of outcomes upon a measurement. So things are no longer binary, right, in these continuous variable settings if you want to know the precise syndrome. Sure, you can discretize it to some precision, but you're still going to have to probably do more than 2 different outcomes, right? That's what these codes were developed and intended for. And this is what I thought as a theorist. But then in the experiment, they just said, forget all your theory. We're just going to extract the first bit of a continuous syndrome. And it actually wound up working, and they wound up getting beyond break even. So this is something I'm pretty dumbfounded by as well, how you can approximate to the degree that you just get the first bit out and it still winds up working. Granted, that's not as simple as the schemes that they did, but those types of flavor of schemes that break down the continuous nature as roughly as possible actually wind up working in the end is very interesting to me. So speaking of experiments, here's maybe not an up-to-date. I think the up-to-date should be on the website, but here's a more or less up-to-date version of all the different realizations of encodings. And so you can see some of these encodings have been realized in photonics, microwave cavities, and even trapped ions. So many of those technologies I showed you in the previous slide are actually pretty prominent and have a high degree of control to realize these codes, including measurements. And I guess the two that were highlighted before are these microwave cavities experiments, which did wind up sort of preserving the logical information more than the physical memory rate would allow without error correction. There's lots of companies studying these things. There's these cluster state approaches here, and there's a sort of alternative cluster state approach here. And then these guys, and I think these guys are going to do some sort of cat qubits and concatenating them with some discrete variable code. Okay, now let's think of the noise. What are the actual physical noise models for these physical systems? So I mentioned noise operators that I can expand any physical noise operator in terms of that are sort of compatible with our Cartesian or angular bases that I've used. Now let's actually look at what the noise operators are in real life. So there's to me, 3 big channels, and I sketch out here what they do to a coherent state. The loss or attenuation channel just dampens the coherent state. If you have a superposition of coherent states, it destroys the superposition very badly. So this picture is very much a schematic, but I just want you to kind of get a picture of where the ball is going here. So the damping channel just basically kind of contracts everything to the center. These names are actually mixed up. I'm sorry. This is the displacement or AGWN, additive Gaussian white noise channel, and this is the dephasing channel. So I put dephasing channel second because it's kind of dual to the loss channel, because now instead of kind of contracting you along a radial direction, it diffuses you along the angular direction. That's called dephasing. And the displacement channel is just diffusing you everywhere linearly. And if you look at Krauss form of these, you can write them down. What's interesting about displacement is the Krauss operators themselves are the noise operators associated with lattice Cartesian codes. They're literally themselves displacements. And yeah. And if you look at which one is prominent in which platform, attenuation is often discussed in terms of fibers and cavities. HWN is also discussed in terms of fibers. Dephasing is common in these other platforms, mechanical and vibrational. Okay, so let's do kind of a rough first order idealized comparison of these, of the noise, of how the noise affects our different codes. Yeah.
So I think several slides ago you said something like a bounded physical error. You could always express that as an integral over displacements. Yeah. Is that still true for the noise models that you?
Yes. Yes. All of these are expressible as superpositions of displacements.
Okay. Good.
Because, I mean, it should make sense because the noise has to be kind of physical. This is literally stemming from physics. So it kind of should keep things bounded and keeps things in Schwartz space. And yeah, it even takes some of this. I think this one, it takes something outside of Schwartz space and actually puts it in.
But I'm guessing it's much cleaner to work in this form than it is with the displacement form, I guess.
Well, it depends. Like this one is the displacement form directly. So some of these are compatible, depends on whether you're Cartesian or angular error basis versus whether this does some Cartesian or angular effects. So there's some compatibility and some very stark incompatibility, which I'm about to show you. So let's pick the loss channel, so the one that dampens everything. That's kind of the most common as far as I know. And let's compare, so it's going to have some loss rate gamma. The capacity is 0 at gamma equals 1/2, and we're just going to compare like what happens to different codes. And we're going to pick our nice lattice codes, the binomial codes, the cat codes. Right, you can embed the 412 code by thinking of the 0 and 1 qubit states as 0 and 1 Fock states. Right, so you can put lots of codes in here. And we remember GKP codes were designed to protect against shifts in position. So they're designed against a Cartesian error basis. But this is very much a radial contraction. But nonetheless, surprisingly, GKP codes are outperforming everybody else. Everybody else here, bin and cat, were designed against momentum kicks, so shifts in the Fock state numbers. So they were designed against the angular basis. This is an angular type of noise channel, so you'd think they'd do better at their own game than GKP, but they don't. And one kind of heuristic way to understand the power of lattices is because the photon loss channel is to some degree really a Cartesian channel in disguise. You can convert it, namely, to a Cartesian channel by following it up with another channel, which is just its adjoint. So the adjoint channel, so pure loss will decay you. The adjoint channel, you can guess, amplification will kick you back up. And if you tune the amount you've breathed out to the same amount that you've breathed in, you're back more or less at the same place. However, you combine two noise channels, so you better not have gotten identity because they're noisy. So what you actually get is the displacement noise, diffusion. So if you contract and you amplify, you get diffusion. And displacement noise is exactly the kind of noise that GKP codes are designed to correct. And so you can work out that even if the extra noise introduced by this amplification is supposed to hurt you, even though that happens, GKP codes still do well because the resulting noise channel winds up being something they can handle. And so if you go into the information theory of it, you can show that quantum lattices achieve capacity up to a constant, and there's some work going on for that now against the loss channel. More general channels that are called thermal noise channels, they also do this. We don't know the capacity of the displacement channel, but they achieve the best thing we can find for it. Or they achieve the hashing bound of the AGWN channel, which this should not be surprising. Okay, so I don't know if that was too many codes. Yes?
Yeah, so you mentioned a thermal noise channel. Is that like just Brownian, or is it not purely Brownian going into like, there's like some other kind of reciprocal that's like close to Brownian, where like the reciprocal is like one over like your signal, the frequency has like an exponential, but that like kind of goes into two. So like the signal may not be like totally, Brownian motion thermal, but be like a little less than that. Is that what you were describing? Does it like take care of something that's not totally Brownian, or does it like?
Well, I think there's a relation to Brownian. I forget though. I can't answer your question because I simply forgot. But they do kind of look similar. I'm not sure in the specific way you're saying, but I'll just explain thermal noise. So loss channel contracts you, and thermal noise is just a combination of loss and amplification in a way that stabilizes the thermal state. So the amplification fights the loss, but not too much, so that in the end you kind of have this nice exponentially damped thermal state as the steady state, as opposed to the vacuum. So it's kind of a competition between amplification and loss. And if you tune the amplification and the loss to be the same, you actually get, that's another way to write displacement noise. So there's lots of games you can play with relating these different channels, and it's kind of fun. But I guess the point here is that one thing that's been rigorously shown is that lattice codes are pretty good, even against noise that's not Cartesian, against noise that's polar. Okay, so I don't know if you're overwhelmed or not by how many codes there are. I hope you're not. I hope you're inspired because there's many different bases to play with. There's lots of different geometries, angular, Cartesian, you can fit inside these things. We've mentioned 3 codes that kind of use this Cartesian mindset. If you have a full lattice, you get GKP. If you have a degenerate lattice, you can protect infinite amount of information. There's an angular way to look at the oscillator or the mode, and you can put circles in it, and you get your number phase or even to some degree cat codes. Yeah, you can generalize circles in 2 ways. You can generalize them to spheres, and you get quantum spherical codes. You can generalize them to donuts, and you get, so this I didn't mention. This is another paper we have on the archive that puts the codes Christoph's going to talk about inside the oscillator using this angular number phase formalism. And there's this third class of codes that I'm not sure how to pin down to a geometry that just winds up kind of being digital and spaced apart in Fock space. So many of these are groups. If you know lattices and circles and 1 sphere, well, 3 sphere and 1 sphere are groups. And there's actually a group-based formalism that you can use to kind of generalize all of these different structures. I don't know, we call them group GKP codes, but that if you can kind of you can use them to develop codes for any group so that they're applicable to these 5. But some are not groups, right? Spheres are not groups in general, and so there that really opens up the sort of questions to how to develop and generalize those codes further. So as I mentioned, classical code words are just some spaced about elements of some alphabet, and the alphabet can be, you know, fields. Everybody loves fields here in classical. They can be rings, so in quantum people like rings more. It can be the reals, which is something I mentioned, or it can even be a finite group. And quantum code words can similarly be developed for any of these alphabets. But what's more, what about the ones that aren't groups? How do we do that? So there's lots of directions here to try to develop things because as I showed you, some of these structures are in fact relevant to physical platforms. Yeah. Yes, yes. So that group GKP formulation from the previous slide was sort of the main idea behind that, taking care of the non-commutativity and still making sure that you can do error correction. Yep. So right. So there's other interesting geometrical objects that are in groups, and there's no general formalism besides this kind of canonical CSS construction that I sketched out in the beginning that's really been formulated for these things. Okay. Future directions. I think it would be nice to really utilize the entire multimode space. So spherical codes, for example, we try to do that because they, you can't fit a 4 sphere in 1 mode. You need 2 modes, right? So the intrinsically multimode encodings are missing. There's not a lot around. I mentioned this kind of simple way to partition classical code words and superpose them to get quantum codes. The superposition is uniform. Anthony, for example, will talk about a non-uniform superpositions of coherent states, for example. And those are kind of, to me, kind of like a non-CSS stabilizer code analogy, right? Because now the coefficients can be anything. Nobody's looked at codes that don't come from stabilizers. So the displacements in the GKP code, they commute. But you can, in principle, just drop down any lattice of coherent states you want inside the mode. And I don't know what happens if you do that. Do you get any error correction? Can you decode, etc.? Code bounds are deeply missing. We have so many different formulations in terms of using different bases. Can we even do bounds for all of them? Or do we have to do individual bounds for individual ones? Do they depend on the noise model more or on the code structure? Regularization. So I mentioned that a lot of these codes can only be defined as a formal superposition of Fock states or position states, and you have to regularize them. There's 2 ways to regularize them. One is you just cut them off, so you have finite superposition of normalizable states. And another way is you dampen the superposition with some exponential. This gives you a set of code words that have some energy that's bounded above by some maximum. And that soft or max energy cutoff, some soft or average energy cutoff, keeps this infinite nature of the code because it still allows superpositions, but it gives you still normalizable states that are defined in this infinite dimensional space. Understanding bounds and things with the set of these states is very different than understanding truly finite dimensional encodings. And there's very little work done on that, and we are trying to develop that a little bit. There's, pick your favorite qubit primitive. I guess you could make a living trying to map favorite qubit primitives. I guess we did kind of do that with designs that I have to mention because this is very interesting result by my student postdoc, continuous variable designs. But there's many different other favorite things that you all love that could potentially be ported over to the oscillator to continuous variable freedom. So maybe there's other code classes. We're kind of starting to exhaust Cartesian and angular things, but maybe there's other things you can slip into this continuous variable space. So with that, I want to conclude and leave you with these quotes. And thank you for your attention.
Thank you, Victor. Any question?
Yeah, sort of, you gave a perspective stemming from sort of space, sort of point of view. So you have space is a code, is a space that you design, but in reality, a lot of it was developed based on the experiment because, some of the codes were more convenient for some practical reasons, whether you measure, whether you can do repetitive measurement in these settings. And can you go back to your summary table and sort of give the perspective, what you don't have, it doesn't have to be comprehensive, but sort of what are good things about these codes for some particular reason, sort of where they have been used or something. It doesn't have to be very exhaustive, just sort of give us some pointers.
Well, I would say not all of these were developed with any experiment in mind. So GKP codes were not, as far as I know. The experimentalists thought they would never exist. CAT codes, on the other hand, were developed by quantum optics theorists. So they were kind of motivated by the physics that I was mentioning to you with this Lindblad that have been long-standing for over 50 years in that community. So there's various motivations that these codes have. Experimentally, these have been, so these are the ones that these CAT codes give you break-even performance. These give you beyond break-even performance. The decoder they use is not just this simple extract the first bit of syndrome. There's also some reinforcement learning involved and very complicated pulses used. So it's not, there's a lot of interesting math behind that work. These are also developed with experiment in mind because they're strictly finite support. However, the coefficients here are very kind of like ad hoc from the point of view of experiments. So it's actually kind of hard to stabilize those codes to develop them. And as I was mentioning before, these guys, so analog stabilizer codes wind up being hyperplanes. I didn't mention this, but now I am. And they are relevant to, so they're kind of very simple because they're based on these kind of Gaussian primitives or like Clifford-like primitives of the oscillator that everybody kind of has at their disposal. So, however, they're not very amenable to noise because the metric they use is the weight and not the total displacement. So they don't protect very well. Yeah.
Is there a way to understand fault tolerance and logical computation in this that's sort of, like, I think you've given a really nice picture and you've motivated everything. It's like, oh, I just have this degree of freedom and this conjugate degree of freedom, and it's sort of, you gave like this beautiful coding theory picture. Where does fault tolerance and logical quantum computation fit into this? Like, how could I say, oh, here's a logical gate and here's why it's fault tolerant?
There is no universal formulation of fault tolerance, but some of these have related formulations. So for GKP, your noise model is displacements. Thanks for the question. But in generally, this is a very big, important open question. I should have put that in the summary slide. But for GKP, for example, your noise model is just sufficiently small shifts, and your gates have to not amplify those shifts to be sufficiently too large. Okay, that's pretty clear. Now, I guess for analog, it'd be a similar thing with weight. For spherical and CAT, everything's on a sphere. As long as the radius, as long as whatever gate you're using doesn't deflate the sphere and things become too close. so that they're not resolved, so that they are resolvable, and so, or sorry, not resolvable. As long as your gadget doesn't deflate the sphere and you wind up moving isometrically around the sphere, things work out.
So there's also a notion of like spread of errors in fault tolerance, right? So I don't know, it just sounds like it's an open question.
Totally is an open question.
Okay.
But I just wanted to give intuition behind this bias preserving gates. They work because they're based off of isometric rotations on a sphere that doesn't deflate. So the distances are preserved. Yeah.
Yeah, thanks for a great tutorial. So you talked about this loss plus amplification becoming displacements, which the GKP can handle. So I've heard some people say that for the dual rail, like loss kind of becomes erasures. So, and I have more generally, like if I want to directly design codes for loss, how would I go ahead in simulating it? Like for poly errors, we know how to sample poly errors and run like noise simulations, but for loss, how do I come up with the simulation framework?
It depends on which underlying space you use. If you're trying to use a single mode, then you can just kind of directly simulate the loss channel as long as you don't have too many Fock states in the mode. If you're doing a lot of the bottoms of a lot of modes, then you have an exponentially growing Hilbert space. Then you have to do something more clever, like converting them to erasures or doing some analytics, because brute force simulation is not gonna scale very well.
So under what cases can I think of loss as erasures?
Well, I think the one you were alluding to, when you just use the first 1 or 2 or 3 Fock states of each mode, and then the loss, I think in some of those cases the loss basically doesn't have very far to take you, and it almost immediately annihilates you, right? Because you go 2 to 1 to 0 to the 0 vector. And so as long as it's close to something like that, then you can kind of just discard that mode and think of it as erasure.
Is that heralded this?
Good question. This is getting out of my territory. You want to talk to Alex Kubica about loss to erasure conversion?
Thanks.
That's a good question.
You had a question. Okay, good.
And this is pretty related to what Steve was asking about, but is there an kind of analog of a simple noise model that includes roughly most of the things that you think are important, like circuit noise for discrete variables, for which there's like even any kind of threshold theorem proven for bosonic codes?
Well, so single mode codes are purported or claim not to have a threshold. That's usually the belief, because it's infinite dimensional, but it's not the same kind of infinity as when you scale up a multi-mode or multi-qubit system. They do have concatenations, so you take your physical qubits, you substitute them, put them in cat states or put them in GKP states, and then you do a surface code on top of that. Then those do have thresholds.
So threshold, but
Code capacity thresholds.
Yeah.
Yeah.
I'm curious if you can like even bootstrap the standard threshold theorem proof based on some rigorous noise model for a bosonic system. I mean, I don't know. Maybe that's already done.
Nothing is coming to mind. Maybe somebody
I
else.
think if you were allowed to encode qubits, concatenate into qubits, then you could do this, because you could dominate it by a stochastic error model, and you could apply existing theorems. I mean, I'm not claiming this would be easy to do, but it seems doable.
It's doable, but I think he's right. It hasn't been
I don't think,
done.
not rigorously, I don't think so.
There are
Do it in the coffee break.
there are issues with sort of soft degrees of freedom because they are not as digital as Z2 codes, for example.
Just to repeat for YouTube, there are issues with soft degrees of freedom, Leonard is saying, but you guys come pretty close. They do a StatMech mapping for GKP codes concatenated with surface codes, and it is kind of a pain.
But that could be, you could dominate that noise with, what does Chris Fassy call it, like local noise, or whatever it's called, right? Noise so that events inside some region E are bounded by P to the E, where P is now a parameter. And if you can just find a bound for that, which you should, because the StatMech model should have exponentially decaying correlations. So there should exist such a P. And then if you tune down the noise in the Baire model, the mode model, sufficiently low, then there will be a sufficiently small P. And then this mapping should go through when you do the sort of standard threshold theorems I think it would need a lot of work, but I think it's probably
It
doable.
should, but the difference is that with sort of, if you try to do it fault tolerantly with measurement errors, then sort of you get the gauge model, and which is different from the regular StatMech models. Whereas, and so there is a difference in sort of local order parameter, etc. Whereas with regular codes, you can just map repeated measurement into one big code, and it works just as well. So there are basically technical difficulties where it's not one and the same thing, I would say.
Sorry, could you comment on like the physics of measurement errors? What's the relevant perception for measurement errors? What difficulties in making measurements?
Well, there's natural precision issues because the thing you're measuring is real valued. So you have to measure it to only some precision, and then there's errors in that. That's the one thing that comes to mind.
Is it like some phenomenological measurement noise model that people have?
Not something I've played with a lot. I like the idealized measurements that give you the real number, because those are very nice. But yeah, I haven't played with approximations to them.
Yeah. So just one last question.
One last one. So when we're zooming out to the architectural picture, right? What's kind of the selling point of these qubits? Because what I'm hearing is like it's not a TLS, right? So you have to go into a Q mode, right? Logical operators are not really clear. I don't know. I'm not a physicist, but aren't modes kind of big, like physically, right? So what's the vision on like an architectural kind of bigger system level perspective here?
Well, those are valid points. Maybe not all the modes are big. This goes back to kind of my third slide that some of these systems you're going to have to use. So for example, if you can't fit everything into one big fridge, you're going to have to connect fridges. How do you do it? Usually people do it with fibers and optical interconnects. So those are modeled by this. So from the communication perspective, it's something you're inadvertently going to have to consider. It's a valid point, especially in the microwave cavity case, that 3D microwave cavities, the ones with the long lifetimes that they got to work for beyond break even, are pretty big. And so that's something they would have to take care of. Gates for lattice Cartesian codes are actually not so bad. There, it's kind of a similar qubit paradigm. So Gaussian operations, which are things that preserve isometric rotations and translations that preserve the lattice, give you your Cliffords. And then there's some extra magic you have to inject. For these, it's kind of upgraded now. Instead of linear, there's no linear things, there's only angular things. And so you have quadratic gates here. But that's where the noise bias preservation comes from, the fact that you're on a sphere. So there's also benefits for that. Yeah, I can show you the other slide after the talk. There's a couple other things I probably not mentioned.
Okay, let's stop here and thank Victor again. And the next talk is at 10:30.